So, hello, welcome to class. Today we're going to be doing a lab to find the speed of sound. Um, just before we start this, kind of a reminder of upcoming things. So again, you will have a test posted on Wednesday over what we're covering. Again, that will cover standing waves on strings, the wave equation, speed equals wavelength times frequency, or interpreting wave graphs. You'll have the Doppler effect, and you'll have intensity questions. Yes. Sorry, I blinked there for a second. So yeah, those are what's going to be on the test. I'll post the answers to the review after this, so that will go up on Google Classroom. And we will have tutorials tomorrow at, I think, 1. I forgot the exact time, depending on what the meetings are. But yeah, I'll post that tomorrow. So there's that. Any late work, make sure you're just getting that in. Get in what you have. Don't let getting a perfect assignment get in the way of getting something turned in. This is kind of how I'm telling, are you like doing all the work and keeping up? So just kind of get in what you have. If you have some things that aren't fully complete and you're not certain, just get that turned in. Probably the biggest thing to get turned in is that take-home quiz. Just please get that done and turned in. So those are upcoming things. Any other questions on the upcoming things this week?
Mr. Beverly,
Yes.
if we don't have a ruler, is it cool if we use a tape measure or no?
Yeah, you can use a tape measure. Any length measuring device. And if you're really can't find anything, just find something standardized. Like if you need to, you could use like the length of a dollar. I mean, I don't know the exact amounts, but you can Google how long is a bill, or how tall is it, how wide is it. So anything like that. Um, if you're really at a loss, you could also, if you have college wool paper, just Google how wide is college wool paper for whatever brand. I mean, there's a lot of random things that you could figure out. So I know some websites have rulers that you can print out based on a normal piece of paper that you can print. So yeah, just anything like that should work. All right. So
The school ID is about 2 inches wide
the
by 3.5 tall.
what?
A school ID is 2 by 3.5.
Inches?
Yeah.
So a school ID is 2 inches by 3.5 inches. So yeah, things like that. So if one person has the water bottle or any sort of bottle, and the other person has a ruler, and you're not at the same space, then yeah, the person who has a ruler can just measure something that the other person has, and you can use it like that. And then yeah, just kind of to the best of your ability, we're trying to measure these things. Another thing is you could look up a length of paper and then fold it and figure out what half a length of paper is, and then a quarter length, and just fold the paper a few times and use that. I mean, just be creative if you really need to. So the things you should be getting right now is a ruler, water bottle, or whatever type of bottle you had. As long as the bottle resonates when you blow across it. So some people were trying to do this earlier. Kind of the key is you want some of the air to go across with your bottom lip on the lip right at the very top, but some of the air needs to blow into the bottle. So part of the air needs to go into the bottle to make it resonate like that. And then, again, you need to pull up this Piano Tuner app, Pano Tuner. It should be free on whatever app store you have. There's a free version and an ad version. Just get the ad version, and if ads really frustrate you, then just do what I did and put it on airplane mode. Then it won't show ads anymore. So, any questions on the supplies?
Do you have to be in a group, or can you work on your own?
If you can't find a group, you can work on your own. I suggest working with a group as much as possible. But yeah, I'm not going to force you to work in a group. I know how difficult it is working as a group. Anything else before we get started? All right. we're going to be looking at this. So we have tubes. Now we've talked about standing waves on a string, and that's all that's going to get tested on this upcoming test. But that's not the only type of instrument that can resonate and make a noise. So we missed all the other types of instruments like wind instruments. So wind instruments behave similar to this. You have air resonating inside of the tube. Now, I'm not going to go through this and make you write these out and do math with this, so I'm just going to tell you what it looks like. So we're going to see the fundamental or the first harmonic inside of a tube like this. It's going to look like this. We're actually going to have a wave that looks like this, where we have an antinode at the endpoint and a node here. So we're going to see in one antinode and one node. Again, don't worry about this so much. This isn't going to be on your test. The more important thing I find of this is using your equation and drawing the graph. All right. So how many waves do I have here if it goes from an antinode to a single node?
A quarter?
Yeah, that's a quarter of a wave. A full wave would have to go to the middle and then all the way back. So this is one wavelength, but we only went from here halfway to the other side. We didn't get all the way to the other side. So we're only looking at 1/4 of a wavelength. So for this experiment that we're doing, we're going to see that 1/4 of a wavelength is going to be equal to the length of that air column. All right, so we can fill up our bottles to different amounts. So we have our bottle here. Let's see this. There we go. So we can see the bottle filled up to different amounts. And so we can measure the height of these. Again, let's try to put this in centimeters. So I can measure the height from here to here. So from here to the top of my tube. Here where this is a little bit slanted. So I see about 10 centimeters on mine. It looks a little bit different on the video because the camera is slanted. So I have a 10 centimeter air column here. This one is about a 13 centimeter air column. And then this one is much longer. This one's about 19 centimeters. So that's what we're using our ruler for. So let's start with that 10 centimeter one. So I could say this one, I know the length of the first tube is 10 centimeters. But what do I want that to be in? Not centimeters, but don't want to use centimeters. We're going to use
Meters.
meters. So divide this by 100 to get 0.1 meters. All right, so I know the length of my tube. But length isn't the thing I really care about in my wave equation, right? My wave equation is the speed is wavelength times frequency. So like we saw here, if we're in our first harmonic, which is going to be the easiest one to make, by the way. So when you blow across the top, it's really hard to make not the first harmonic. So how do I get the wavelength for this? The length is 1/4 of the wavelength. The wavelength equals four times the length, right? And again, this whole thing, you're not going to have to do this on your test. This is why I'm just kind of giving this to you. So we're going to have to multiply this number times 4. Our wavelength is going to be equal to 4 times that 0.1 meters. So my wavelength is going to be 0.4 meters long here. And again, this is really similar to a standing wave on a string. my wavelength depended on what harmonic I was in. I drew out my wave to figure out how much wave I had, figured out the length of the string, combined those to get wavelength. All right, so I know wavelength for this bottle. What else am I going to need to figure out how fast sound is going through the air?
Frequency?
Frequency. So that's what our tuner is for right here. So I have my tuner app. I'm going to play my note. Kind of hard to tell. It was bouncing around. I saw 397. 397, 398, somewhere right around there. So my frequency was about 398 hertz. So I could combine this together to get the speed of sound in air. So what would I do? Can multiply these together. This is going to give me a pretty low value. There are some effects going on here that are going to cause issues, but we'll just roll with it. So what speed did I get here? So yeah, that's saying 159.2. Here, let's just see something real fast. Yeah, it is about that. All right. So yeah, so we are getting a lot lower value here. I haven't fully tested it, but I suspect as you get closer to here, as you get close to the top, it's probably going to have more and more effects of being off. But as we get longer and longer, it's probably going to be a better estimate. We'll see. Let's see. I didn't actually calculate this. 0.4 times. Yeah, 159.2. So we get a low value there. That's not the end of the world. We should see better results when I have a shorter water bottle. So when I have more air in there, I suspect it's going to be a much better result. So we do this. That's one way of figuring that out. But we're not going to just sit here and use our equation. What's another way we can analyze data other than just substituting values into an equation? I mean, if you read the procedure, I tell you what to do. We're pretty much just walking through the procedure at the moment. We could draw a graph. What's something I could measure from a graph? Something I can calculate from a graph. Speed. I mean, we are going to use the graph to get speed. But what are mathematical operations I could do to analyze a graph? More looking for the math term of what I could do. What could I find? I could find average. Or I could find slope. Yeah, it's slope. Slope. What over what?
Y over X.
Y over X, rise over run, change in Y over change in X. Now, I want my slope to equal speed. All right. So my Y value, I'm going to choose to put wavelength right here. So wavelength in meters. So that's fine. I have y. All right, so what am I going to put on my x-axis?
Frequency?
Okay, so let's look at doing frequency. So I do wavelength divided by frequency. Does that equal speed?
No. That's the inverse of
Let's
speed.
see. It's not the inverse of speed. Close, but something's inverse. Which one of these needs to be inverse?
The frequency.
So if I do 1 over frequency right here, divided by 1 over frequency. Now if I divide by 1 over f, now that's going to be the same as multiplying by wavelength times frequency. So I could do 1 over frequency here. But what's the other name for 1 over frequency?
Period.
So we're going to graph period here in seconds. So that's why we're graphing versus period. So we'll graph our data point. We'll hopefully see a line. I suspect it might not be perfectly linear. We're just going to assume this is linear. There's going to be a few effects that we're not accounting for here, but that's okay. So we get our graph. We do our wavelength versus period for blank. Right? Remember, graphs need a title. So we're going to use this graph and we're going to measure the slope to get our speed of sound. So we go through, we get a speed of sound. Speed of sound experimental is going to equal the slope of that wavelength versus period graph. Now, how could I get an actual speed of sound in air?
Do we use the formula?
Speed of air. Which formula?
The 332 plus 0.6.
All right. So 332 meters per second plus 0.6 times our temperature in Celsius. Now, let's see. My thermostat says it's 71 degrees in here. Temperature equals 71 degrees. So I just put 71 here, right? $71, so I put 71 degrees.
No, because that's Fahrenheit.
That's
You need Celsius.
Fahrenheit. Yeah, so what do we do to get it to Celsius?
We say screw science and use Fahrenheit instead of Celsius.
Isn't it like 5 over 9?
Okay,
9 over 5?
so not screw science. Metric is definitely way better than what America passes for a system of standards. So 5/9, we end up with a smaller number, but we also want to get the freezing points the same. So what's a freezing point of Fahrenheit?
32.
32. So let's get rid of that 32 degrees. That way, because we know 32 degrees Fahrenheit equals 0 degrees Celsius, so we're getting rid of that offset, and then using our 5/9 here. So my house is at 21.67 degrees Celsius. All right, so for me, let's put this in here, 21.67 degrees Celsius. So in my house, it's right around 345 meters per second for the speed of sound. So the number I calculated up here was off. Again, I highly suspect that that's because we were close to the top of the water bottle. So we're going to do this for 8 different water levels. Let's try to do kind of lower water levels, because I'm pretty sure what's happening as you get close to here, it's going to be worse and worse as the thing narrows. It's going to be a lot more complicated interactions going on there. All right, so any questions anywhere on this procedure of what I did? how we went through how I'm wanting you to analyze your data. Could I move my paper up? Yeah, I could. Yeah, sorry, I had water bottles in the way. So I figured because that was my part of the lab, I'll probably just leave this up, keep recording. So yeah, if you're doing this just from the recorded video, I've already gone through everything. I'm probably just going to sit here and let it keep recording, and y'all can work through and ask questions as you work. So if you're wanting to get with your group, you could ask that now.
Mr. Beverly, have you heard about the online NIMSY sessions?
Yeah, I haven't actually read into the online NIMSY sessions as much. I think if you went to one of them, then you're good. And it's also like on demand. Yeah, I need to look into that.
Because it says like, I don't know. One of my friends showed me it. It's like AP Physics 1. So like, I don't know if it's necessary for me to join that.
It would be good to join it, especially for their rotational motion review. But yeah, just kind of look through it, find the things you don't know. That would be the most useful thing. So we have to find 2 ways of doing this for the lab. So we're only doing this one way. So we're going to do experimentally. We're going to get our speed of sound experimentally from our graph of wavelength versus period. I guess if you mean the second way of doing it, normally we find the speed 2 ways so we can compare values. So we're going to get our actual value. I mean, actual, it is still a measured value. Either go to your thermostat. If your air conditioner is on or heater is on or whatever is on right now, you should be able to read the current value on it. If you have an older system that's just set to a value, but your air is off, then it might be better to go and just find weather temperature and find the temperature there. You're welcome. I actually think this might be too much dead time. I think I'm going to stop the recording here, but I'll stay here for any additional questions. So I'm going to stay online but stop recording. So again, just a reminder of things coming up. Test on Wednesday. I'll post the answers to the review real soon. And then we will have a tutorial tomorrow in the afternoon. And I can either talk about the lab or test review, things like that. But yeah, just kind of keep up. If you haven't turned in your spring break assignment, please get that turned in as soon as possible. And any late works, just get that in, even if it's not fully finished, even if it's not done perfectly. If you're turning in just something, then I can justify kind of giving you grades and say like, oh, you're kind of moving along and keeping up. So don't let it be it's not a perfect assignment, so I'm not going to turn it in. Just kind of get in what you have, and as long as you're turning in assignments, you'll be doing okay, right? So for everyone watching the recording, have a good rest of the day.